Good morning, good afternoon, and welcome to this month's Revolution.Aero Town Hall, kindly sponsored by BAE Systems. Today's topic is safety considerations in the design of propulsion-scale aircraft battery systems, a topic which is integral to the future of advanced air mobility. This is one of the most crucial parts for the industry to successfully transition from existing aircraft to electric vertical or conventional takeoff and landing. The format for today's town hall is slightly different in that three experts will take us through battery technology and some of the issues therein, and then we'll answer a few questions. They would especially like to take questions from the audience, so please use the Ask a Question function located at the bottom of the video, and we'll try and get through them as many as possible. We'll try and get through all the questions. So without further ado, I'd like to invite Josh Stewart, who is the Principal Power Systems Engineer for BAE Systems. And Josh is going to take it away. Over to you, Josh.
Hello. Yes, thank you for your attention. And as Yvonne said, my name is Josh Stewart. I'm a Power Systems Engineer with BAE Systems. I've worked with BAE for 10 years. And my area of focus is really in high voltage battery system design, cell modeling, cell selection, battery testing, especially thermal runaway testing, and even high voltage cable design and high voltage system architecture. So the topic as was already mentioned, is safety considerations in the design of propulsion scale aircraft battery systems. And this is a very important topic. I think we're probably all familiar with, some of the safety considerations with batteries. We've all probably heard about tablets catching on fire, and when we take these batteries up to high voltage, and we've taken them into the automotive field, we see electric vehicles catching on fire, and then when we take these battery systems up to altitude and up on aircraft for propulsion, there's a whole nother level of risk and considerations that go along with it. So it's a very important topic, and I believe BAE is uniquely positioned to help understand some of these considerations. And so first of all, before I get into some of those specific details, just a little bit more about BAE Systems and why, BAE is positioned to really transform the future of aviation. There may be some of you who don't know, but BAE has a long history in working with high voltage power systems. We have over 14,000 electric hybrid systems fielded, operating worldwide. And so this is, things like hybrid buses. And we actually have all electric buses as well. And there are also marine applications as well. And BAE was actually the first company to field a commercial lithium-ion battery pack. And so we've been doing this work for decades. We also have experience pairing our propulsion and our power systems with renewables, with fuel cells, and other power sources. We've also done a lot of work in military ground vehicles, electrifying military ground vehicles. So we really understand how to take our power electronics and make them extremely high reliability. The military ground vehicles, of course, have a very harsh environment. The ground transit vehicles have an 18 to 20 hours per day operating window, and they run for 10 to 20 years. So we're talking like a 50,000 hour service life. That's actually pretty comparable to commercial aerospace. So these electronics are designed for extreme environment and high reliability. So in conjunction with that, BAE brings to the table our more than 40 years of work developing fly-by-wire flight controls and engine controls. So these are certified electronics for aircraft. We have the experience to design these systems, to get them certified, and to produce them. And what we're doing is we're really bringing all of that experience together to really make a difference in this space, and to help answer some of those challenges from those safety considerations. So a little bit more about our rich legacy when it comes to energy storage. We have a lot of experience with, from the ground up, bringing a battery cell in-house. And we've been doing this again for decades, bringing batteries into our facility, doing cell characterization, doing pack assembly, and actually automating that pack assembly. We know what it takes to build up these high voltage systems, and the safety issues that are there, the high voltage dangers that are there, what personal protective equipment is required to handle these systems. We understand the quality controls that need to be in place. We understand, the testing that's required to basically ensure that these designs are safe and that they're going to perform as expected, and they're not going to do damage to the system, and that they are not going to be hazardous to personnel. We also have the field support system in place to maintain these battery packs as they age and throughout their life. So this is from the legacy that we bring from the ground vehicle transit side. But then moving into aircraft electrification, we've actually made a significant investment in this space. We've gone off and we've brought in capabilities. We've developed a lab where we actually are equipped to support low rate research and development of new batteries, new battery pack architectures, all the way up through low rate initial production. So we have the scalability to actually produce aircraft battery packs in this lab. And we actually have the space available on our campus to expand to full rate production of these large energy storage systems. We have brought in robotics as well. We've brought in access to over 2 megawatts of power. So we can actually do charge and discharge of our battery packs right in the lab. We have developed test equipment as well. To the bottom right, you can see a picture of our grid-tied inverter. What this allows us to do is actually operate in 4 quadrants, and we can push and pull power off the grid for the testing of our battery systems. And actually, it's this piece of test equipment that is very similar to what we're offering in the battery charger and vertiport field as well. So you can kind of see that there's a lot of overlap with the technology. So we can do cycle life testing, performance testing of battery cells, all the way up to the pack level testing and analysis. We also have environmental chambers. We have EMI chambers. We have vibration test chambers as well. We have over 1,000 hours of thermal runaway testing experience. So we've spent a lot of time doing thermal runaway testing, and we'll get to that later. But I think the point here is that BAE has made a significant investment, and we are bringing our experience to bear to meet the challenges of safe electric propulsion of aircraft. So the three areas I really want to talk about are ground fault and arc flash, and the safety challenges associated with that, thermal runaway, which is a hot button issue, not to pun, but and then the loss of critical power, and that's sort of anything that would cause a battery pack to go offline in a high voltage aircraft power architecture. And there's a number of things that play into that. So I'll just get into the first one, and that is ground fault and arc flash hazards. The the first thing is that we need to understand what an arc flash is. So an arc flash is when you have high voltage that jumps through the air to ground or to another voltage, and it actually superheats the air and creates an explosion and a tremendous release of thermal energy. And so this can produce extreme damage to the battery system, to the other parts of the high voltage system, and it can be very dangerous for personnel as well. So really understanding what the arc flash potential of the battery system is very important. So we need to do an analysis at the cell level, at the module level, at the pack level, and then this leads into designing of fuses and contactors as well into the battery architecture. So some of these fuses are going to be off-the-shelf fuses, but there are others that are going to be custom designed. So the ability to analyze, to design fuses, to test them, and to understand the arc flash potential of your battery pack over its operating range. So if I can just give an example, you might design a battery pack, and the fuses are designed so that the short circuit current opens the fuse at room temperature. But then you take the same battery pack and you take it down to freezing temperatures. And what happens is the internal resistance of the battery cells actually increases as the temperature decreases. And so now what you have is the same battery pack, but its short circuit current is lower than what the fuse will clear at. So now you have a sustained arc flash taking place on the same battery pack with a fuse that will not clear. So you really need to understand your battery pack over all of its operating conditions and the whole envelope, and make sure that you're covered with fuses and the overall high voltage architecture of the battery pack. Understanding altitude effects, the voltage breakdown of air actually decreases as altitude increases. So, insulation and clearance and creepage allowances that are acceptable at 0 feet of elevation may not be enough at higher altitudes. So this isn't going to come into play so much for lower altitude aircraft, but for high altitude aircraft, this is significant. Even understanding the partial discharge susceptibility of the interconnects, the cables, and then the manufacturability and the handling of battery packs, and really understanding the kinds of methods that are going to be required to safely and consistently build these battery systems. And that involves bringing robotics in and quality control as well. So next, thermal runaway. Before I look at how do we mitigate that, just a little bit about it in case there are those who aren't familiar. Thermal runaway with batteries is something that happens when there's abuse to a battery. This could be mechanical abuse like penetration or crushing. It could be electrical abuse such as overcharging or over discharging a battery cell. And then thermal, overheating a battery. And in any one of these cases, what ends up happening is a short develops between the anode and the cathode in the battery. So whether it's like a dendrite that forms and pierces through the separator, or the separator melting, or whatever it might be, a type 2 internal short develops inside the battery. And this leads to tremendous heat generation in the battery cell. And it leads to a temperature rise, which then increases the reaction rate, which leads to more heat generation. And it's an exponential increase in temperature and also the dissipation of heat. So we have a tremendous amount of heat that's put into the battery pack, and extremely high temperatures. And so in an ideal scenario, what would happen is, well, first of all, you wouldn't have thermal runaway, but if you did, that battery would just cool right back down and everything would be okay. But what can happen is there's so much energy release and so many things happening that it can cause another cell, maybe the adjacent cell to the one that is experiencing thermal runaway, to then it can go into thermal runaway. And like a row of dominoes, this just propagates through the entire battery pack. So this is called propagation, where one thermal runaway leads to another. And this is something that we really need to understand. So what I have shown on the upper right is a plot of one of the tests that we ran. We might call this a successful propagation mitigation test, where we were trying to prevent propagation from taking place. And so we caused some thermal abuse to a battery cell. We heated it up, and then around 120 degrees C, the cell vented. There was a feature in the cell that allowed that high pressure to escape, which is actually a safety feature that can be very important in the designing of these battery packs. And then a little bit later, as we continued to heat it, this cycle began, and there was self-heating that took place and an exponential temperature increase. And the cell actually gets to around 600 degrees C. And the gases and the flames that are emitted are can be as high as 1,200 degrees. But then in this case, the cell cooled back down, and the adjacent cell remained at a safe temperature, remained below 70 degrees C. So this was a good successful attempt to stop propagation. So that's just a little bit of information to help understand thermal runaway. So how do we mitigate it? We start by selecting cells that are designed for safety, that have features in the cells that will cause the electrical connection to open up if something goes wrong. Now, of course, we can't count on that always. So then we need to go up to the module or pack level and have features there that will prevent thermal runaway from making the battery unsafe. And then we use modeling and analysis. And this is really important because, first of all, it helps us to understand the physics of thermal runaway. So we use a number of different tools. And at the end, John Harrison is going to present some of the work that Gamma Technologies is doing to help companies like BAE and others who are getting into this space to be able to analyze thermal runaway. And then advanced materials. I can't get into too much of this without giving away some proprietary information, but advanced materials that will really help prevent propagation or contain propagation once it begins. And then advanced control strategies. Again, some things that we're doing to cleverly isolate cells and prevent propagation from taking place. Thermal runaway testing. DO-311A is the minimum operational performance standards for battery packs on aircraft. And we are intimately familiar with the details of that standard and understanding how to instrument those tests, and run those tests and demonstrate successful containment. Humidity, vibration, crash shock, these are all the environmental tests that are also required through DO-311A and also DO-160, and going through all of that testing to make sure that the battery pack can survive in harsh environments. Propagation versus containment, these are two sort of strategies that are allowed by DO-311A. One is that you would try to stop propagation from taking place in the first place. One cell would not propagate to the next. The other strategy would be that you allow it to propagate to a certain boundary, let's say a module or a pack, sub-pack, and then you contain it at the sub-pack level. There are obviously pros and cons, to these different approaches, and BAE is looking at both, and depending on the design of the aircraft and the system safety analysis, one might be more desirable than the other. So now we get to that third area that I talked about, and this is, again, arc flashes and ground faults, and thermal runaway can lead to the loss of critical power, but this is perhaps a little broader category. What I just have shown here is a typical architecture for an electric aircraft. So what we have shown here is a high voltage bus. And typically there will be a number of subpacks that are in parallel on this high voltage bus. Now I don't have shown all the logic of the cross tying and the interconnects and all that's required here. But just at a high level, you're going to have redundant battery systems in parallel. And then you're going to have, of course, a series of inverters also that drive electric motors typically to power the aircraft. Then you're going to have a DC to DC converter also that hangs off the high voltage bus that will provide the low voltage power for avionics and other low voltage loads. And then you'll also have another DC to DC that will provide maybe intermediate voltage for actuators and other loads on the aircraft. Then you'll have a communication between all of the electronics and a power management controller, typically, which will sit over top all of that and manage the power system. And there's definitely a lot of variations with this, but this is just a typical architecture, and hopefully we'll give some context to some of the things BAE is doing to help with safety. So if we lose a pack, we need to be able to safely continue flight. In fact, this is part of the system safety analysis. We need to understand how many subpacks are going to be required, such that if you lose one or two, or whatever the number is, that you're able to safely continue flight and land. And so we'll talk a little bit more about that. But that is the failure mode we're talking about now, is loss of critical power. Okay, so the first thing really to mitigate this is to have a redundant high voltage system architecture, to not have all your eggs in one basket, not to have all your cells in one pack, really to have multiple battery packs that are redundant. And this is really important. And again, this comes down to doing your system safety analysis. You need to have a probability for a catastrophic failure of less than 10 to the -9th. And you can't start the design of your aircraft too early in doing this system safety analysis. It's really going to drive the aircraft power architecture. So in terms of how many subpacks are required. And then there's the selection of components like fuses and contactors, and understanding their failure rates and the number of them. So on one hand, you want to have more subpacks. On the other hand, more subpacks means more fuses and more contactors and more other things to break. And then there's the battery management system. Very, very important to have a reliable and certifiable battery management system. BAE uses a distributed battery management system, and I won't get into too much more detail, but our battery management system is designed to DO 178 DAL-A compliance, and we are experienced with the DO 178 certification process. We have many aircraft controls that have gone through the process and are operating on certified platforms today. And so we're actually starting with a operating system that is reused from a certified flight control. So we're not starting from something that's just off the shelf, something that's automotive. We are starting with something that's already been through that rigor, and then we're taking it back through again, and we're designing it to be compliant DAL-A. And the battery management system needs to track voltage and current of every cell group, state of charge. It needs to look at state of health as well and remaining life, and it needs to detect faults and many other things. So it's very critical that there is a reliable BMS. Accurate state of charge estimation, is so important. That is your fuel gauge. What is the remaining state of charge? And having that be accurate, very important. Something even harder than that is the state of health. We spend a lot of time and a lot of effort testing our battery cells and building models of our battery cells and looking at them in various cycles and various temperatures. And so we use open and closed loop models to predict remaining life. And we do this on vehicle as well. So this is something we're really proud of and is a very important part of our battery management system. Fault and event detection, being able to detect ground faults and measure isolation, very important. If you end up with a low impedance to ground, you can have catastrophic failures in your battery system. One of the worst is a double ground fault, where you actually have two connections, two low impedance paths to ground. And in a worst case scenario, there isn't the proper fusing between those two connections, and it turns into a very high current short, which produces a lot of heat, and it's not good. And then integrating with the power electronics, having the communication, having the fault discretes that report out the important information, having limits and warnings that feed back to the chargers. One of the most important things is that the battery pack will protect itself against bad chargers, chargers that might damage the battery pack, and integrating with the flight control computer and providing the right information to the flight control and to the cockpit. Well, the last thing I'll say before I turn this over to Jesse with Jaunt Air Mobility. I really believe that BAE has the experience to make a difference, to meet the safety challenges for aircraft electrification. We have the experience. We have the pedigree with high voltage energy storage systems for electric drives. We have many years designing and building certifiable flight critical electronics. And we have the advanced techniques, we have the personnel, we have the experience to make all of this happen. So I really believe BAE is uniquely positioned to be a help in this space, and would welcome any further conversations that you might have, and look forward to hopefully answering some of your questions. So thank you very much for listening, and I'll pass on the floor to Jesse.
Josh, thanks so much for that. We have many questions coming in, but we're going to save questions for the end. So next, I'd like to bring up Jesse Crispino, Chief Operations Officer at Jaunt Air Mobility. Jesse, welcome, and take it away.
Yeah, so good morning, good afternoon, wherever you're located. Jesse Crispino, Chief Operations Officer. My background, I've been with Jaunt since the beginning, but my background is largely experimental flight tests for the military, and also program management for aircraft development programs. So what I'm going to do is take what Josh just presented and kind of bring it up a level to the aircraft, and kind of the so what of all those things he talked about. So at Jaunt Air Mobility, we're designing and building the Jaunt Journey. It's a slow-rotored compound aircraft. In our case, it has a single main rotor, and it has propellers and wings. The main rotor is powered at all times during flight. It can hover the aircraft can hover just like a helicopter. However, when it accelerates, that main rotor slows, and what that does is give you tremendous aerodynamic efficiency with reducing the drag on the airplane. It also lowers the acoustic profile of the airplane. The aircraft is going to come with a state-of-the-art fly-by-wire triplex redundant system. It's being designed by BAE Systems as well. You'll notice there's no tail rotor on the airplane. We've taken that single point failure of a tail rotor off the traditional helicopter model and moved the anti-torque out to the wings. So when you size the propellers for forward flight for this particular aircraft, you actually get twice the redundancy, or twice the anti-torque power you would need to provide traditional anti-torque at a hover. So we removed that single point failure of a tail rotor, put it out on the wings where pilots can see it, and made it redundant. The aircraft architecture is basically identical to a twin engine helicopter. And so for that reason, we intend to certify this aircraft to Part 29 standards, and it falls very squarely within that. You can see the rest of the specs of the airplane, but I think we've shown this enough that I kind of want to move down to the next stuff, which is, What's being done today, and how does that translate to the future? So fuel systems have been around as long as engines, and they're historically well understood, and they're very, very robust. Fuel pumps are mechanically driven. They're attached to the engines. They're very, very reliable. When the engine comes off to be overhauled, the fuel pump comes off and is rebuilt. And so it's very rare that you see a fuel pump fail. And if it does fail, you probably have an electric boost pump that lives in the tank ready to pick up that backup mission of delivering fuel to the engine. So again, fuel pumps, getting gas to engines is something we do very well as aircraft manufacturers. Fuel testing. So fuel testing is done every day at every airport to make sure that the fuel is in fact suitable for aviation purposes. The pilot or the maintainer will test the fuel and pull a fuel sample every morning. He'll be checking for contaminants, and he'll be looking for any indications that there was moisture intrusion or water intrusion into the fuel system. The fuel shipment and fuel storage regulations have been around for a long time, and so we know how to keep gas healthy. So the next one would be FOD, right? So there's not a lot that can go wrong with a fuel system, right? So FOD checks. If FOD gets in your fuel tank, that would be bad. But FOD is a big deal on the airplane, no matter where you're talking about, but especially when it comes to the fuel system. If you open up that fuel system for any maintenance actions, you can be rest assured that there will be a check, double check, and probably triple check on that system before it's reassembled, just to make sure that nothing was left in the tank and there's no potential for blockages when the aircraft is operating. You know, how do we get these fuel systems tested and certified? Again, Josh alluded to a lot of this, but it's largely component and bench level testing. You know, we start with a full environmental span of tests that is done on every component on the aircraft. And so every part of the fuel system goes through all those tests. And then we put it all together and we do these ground runs. And that's kind of where you shake out the fuel system for the first time. It's where all the parts kind of meet each other and kind of get to know each other. So by the time you move to flight tests, you're very confident in the fuel system on the airplane. When you're in flight test, there's very little tests that are fuel system specific. It's more like, I call it opportunity data points. You're always gathering data as you're doing other things in the test program. You know, you're always monitoring fuel flow, you're always monitoring fuel levels and what the burn is on the engines. And then you bring the airplane down to the ground, you put it through the full range of EMC, EMI checks. And those checks are designed for all the aircraft systems. But the fuel system is one of them that's being monitored. You might be looking for flashing lights or flickering, you know, low pressure lights in the cockpit when you're zapping the aircraft with different spectrums of energy. But it's something you're testing. You're testing it. And then we hit the aircraft with lightning, and we make sure that everything still works, to include the fuel system. And then in my old days, we would even shoot the fuel tanks to make sure that they would self-seal if a round was to penetrate the tank. We can't have fuel leaking if rounds of different caliber penetrate the tank. So then that leaves us with kind of the only exciting test, if you will, on what we do for legacy systems. And it's called the 50-foot drop test, as most of us call it. And it entails taking the fuel bladder, the fuel cell itself, and then you wrap it with a representative aircraft structure, and you have to drop those, you know, from 50 feet onto a hard surface. And that's a very challenging test. And that's where, the OEMs find a lot of problems, if you will. There's a tremendous amount of hydrostatic pressure in those tanks. And you have to make sure that the breakaway fittings do indeed break away. The fuel is contained. You have to make sure that the fuel system doesn't impinge on the volume of the cabin, right? Because in theory, there could be passengers there, and it wouldn't be nice to have a fuel system, you know, injuring them during a crash or hard landing sequence. And all of this is done to prevent what's called a post-crash fire. And post-crash fires have historically been a tremendously large contributor to fatalities. We've gotten a lot better over the past 20 years, but still, depending on where you find the data, where you look, 1 in 4 fatalities is due to a post-crash fire. So now the battery systems, they're going to need all this same testing and all this same level of rigor, environmental tests, EMC/EMI, lightning. Here's an interesting one, electrical disconnects versus fuel disconnects. Josh talked about all these high voltage lines running around the airplane. Can't have a first responder coming up to the airplane and grabbing something that's hot, right? That's full of all this electricity. So those breakaways that used to be for fuel are now going to have to be made for the electrical system. There's a whole bunch of other like load factor testing that has to be done with fuel systems, thermal runaway. I think Josh has really nailed that well. And the end result is we need the same level of fire prevention and cabin intrusion prevention that we have with a legacy system. It's going to kind of look the same, but in many, many ways, it's going to be very, very different. So this is kind of the high level, if you think about it from a cockpit perspective, and it's okay, it's a cockpit perspective because the authorities they'll still be looking at it from this perspective as well. The legacy fuel system on the left, the electric propulsion system on the right, some of the safety concerns. Again, with gas, not a lot of things I worried about. I worried about the engine going out. That could mean I don't have gas. I worried about the fuel going low. That means I probably need to land the airplane, right? Or need to finish that mission. And fuel pressure low, again, I talked about those backup boost pumps. If they're not already on, you might turn them on. That might make that light go away. And if not, you just go ahead and land the airplane. Some additional considerations that we have with legacy systems is sometimes you get fuel venting. If you overpressurize those tanks, or if you fill them too much, the fuel may come out of airlines, or it may come out of the cap if it wasn't put on correctly. And of course, you can't have fuel going into the aircraft, right, to the cabin or the cockpit. And you can't have fuel going into engine inlets, right? So that would be horrible. So when gas does vent, and I've seen it many, many times, it is a consideration, a safety consideration, and the pilots have to take some action. The CG of the airplane changes as you burn gas, right? So, but it's understood and it's known, and you handle it in your performance planning, right? So the weight of gas, the weight of fuel, and where it's located. And so you can account for that CG burn to make sure you stay within CG limits. It's linear. And then you may have to worry about some cross feeding. Say you have a tank imbalance for some reason. You did a lot of ground runs on one tank, and you may have to level those tanks in flight. But again, those are kind of 9 events. Now you jump over to the batteries. I'm going to this puts together a lot of the things, the words that Josh said, into like the so what, if you will. You have a voltage low situation. It's kind of like your fuel pressure being low, except now you can damage cells, or you could potentially drop a motor offline if it got too low. You have the state of charge, as he alluded to. State of charge is like your fuel low light, except it's not, because you have a thing called impedance. And impedance matters. You may get to a situation where you're at a certain low state of charge and you think you have the ability to perform a maneuver to get home. But at the end of that getting home process, that maneuver requires a very high power application, such as a hover land maneuver or a go around. If you pull too much power with a high impedance, as the state of charge droops and that impedance is creeping up, you might drop the voltage, a transient voltage drop that could theoretically drop a motor offline or cause permanent cell damage. And that impedance changes, as the state of health of that battery changes. We talked about it. These batteries will age. It's going to affect them. Also, the battery temperatures are going to change as the battery ages, right? So, where one day you didn't get the battery hot light coming on, a couple of months later, that same environmental conditions, you could theoretically start to increase the battery temperatures to a dangerous condition. And then you have a multitude of these white lights, I call them advisories, like Josh talked about, battery subpack degraded, battery module, submodule mismatch, right? So you have the packs, you have the subpacks, you have the modules, you have the cells. How much information does the pilot need to know? How much information does the system need to know and manage itself? He talked about that battery management software. He wasn't kidding when he said it needs to be DAL-A compliant software. It needs to be redundant and DAL-A. Your battery management software, in conjunction with those motor controllers, that becomes the FADEC for an electrical aircraft. And FADEC systems have to be certified to that DAL-A assurance, DAL-A compliance. Of course, you could have the motor out. You could have the thermal runaway. We talked about that. Some of the other things, the venting, right? So batteries could potentially vent, and the venting can't happen into the cabin. You need to make sure that it goes safely away from the airplane, and that's challenging when you start talking about different flight conditions, whether you're coming up or going down, where the air is. You can have a thing where the air is ingested as you're descending. Then you have capacity decreases on these battery systems over time. And this is probably the biggest deal. He talked about it, but I'm going to put it in perspective. How much gas you have in the tank changes on a daily basis and changes over the life of the airplane, and depending on what you've done with that airplane. So your performance planning is dynamic and it's not linear. And so to account for a reserve properly, instead of just knowing a time to fly, you really need to know the time to fly and the maneuvers to be performed and the impedance levels on the system. And capacity decreases are going to happen differently across all aircraft. So a Jaunt aircraft in Dallas and a Jaunt aircraft in New York City are going to age. Their battery packs are going to age differently because of different duty cycles. In fact, 2 aircraft operating on a New York City, in theory, could age differently if one is doing just turn and burns to the airport all day, and the other is going out to Long Island, and then get some more rest time. Because how you charge it and how you use it matters. How much gas is in the tank is not linear anymore. Then again, cross-feeding, sometimes cross ties, as he said. We have to understand, how those systems work. Are they automated? They need to be automated to a large degree, so that battery management software, yet again, critical. And then refuel of batteries, which is recharging. I used to just give my credit card to the guys at the airport and say, give me gas, and go inside and get food. And I was confident I was getting gas. It was going to be good gas. It would be fine. It would work just good. But now I have to make sure I'm charging at the correct charging profile. I have to make sure the charger is correct, right? These chargers are going to start off being unique to the airplanes. So I need to make sure that, when it's connected, is charging at the correct charging profile. If something goes wrong, I need confidence that my battery management software sees it and says, no, you're cut off. No more charge. Because you can start to damage things and, damage cells or cause potential fires on the ground. I may also have to cool those batteries as I'm charging them. And I need to make sure that cooling mechanism is operating correctly, is made for that airplane. So the takeaway here is fuel is very, very linear. The times are changing, and electrical propulsion is not going to be linear. And the only way to get after that is with a tremendous amount of bench testing on these airplanes, performance testing, bench testing of the battery systems, performance testing on the airplanes, and modeling and simulation. And so Gamma is going to talk about the importance and what they can do. And it's those type of systems that are going to be absolutely critical to certify these airplanes. And then, again, we're certifying to 10 to the -9th reliability. Not everyone else is. But the reality is that every single aircraft over its life, no matter what configuration, every configuration is going to have a total power loss at some point. We're going to have so many flight hours on these airplanes, it's going to happen. And it might be a total system failure, or it could be a partial system, more than likely a partial system failure. We'll see those where pilots shut off the good engine, right? Or shut off the good motor in this case. It happens. At Jaunt, we're lucky enough to be able to auto rotate to the ground. We have a super amount of inertia in these rotor blades, and we can land from any airspeed or altitude with a tremendous glide range and land with a precision landing that almost resembles a normal landing. And it overcomes the limitations of a ballistic parachute, which is how a lot of configurations will have to get after this problem. Ballistic parachutes work great if you, one, have sufficient altitude for that ballistic chute to deploy, right? It doesn't work well at 100 feet. And then they work well if you are in a level attitude where the ballistic chute, when it deploys, doesn't become FOD into the lifting system. So if you're, off to the side, that ballistic chute may not be the answer. So this will wrap it up. BAE's talked about their history and their experience in fly-by-wire technology. And for that reason, we personally chose BAE Systems to navigate all these challenges. We gave them the battery requirements for our aircraft, and they came back to us. Josh and his team came back to us and said, hey, we can meet this with today's technology. So Jaunt doesn't have to wait for any new cell chemistries or any further advancements in battery technology to be able to design and build this airplane. So that wraps it up for me. Sorry I went long, guys.
Jesse, thanks so much for that. So next we're going to go to John Harrison, an engineer and business development at Gamma Technologies. John, sorry, hope I got your job title right, but I'll let you take it away with the slides now.
Excellent, thank you. So I'm going to conclude the talk here talking about the role of simulation in reducing risk with safety and electric aircraft and so forth, and speak to some of the points that Jesse and Joshua have already mentioned. And we all know that there are safety concerns with battery electric aircraft. We've seen headlines in multiple different types of industries, including not just limited to aerospace, but traditional automotive, energy storage, electric bikes, and things like that. And concerns like thermal runaway. It's a real significant risk to the safety of the system, but also with potential for catastrophic failure. And in order to reduce this risk, obviously there's a tremendous amount of testing that goes into designing the packs, as Joshua had mentioned. But there's the role of simulation is also used to complement the testing when designing these packs to really understand and optimize for safety concerns. Now, there's other challenges that engineers are facing when designing battery electric aircraft systems. Even from the concept phase, if you're looking at it from a safety standpoint, what type of selection of batteries are you going to use? How many cells are needed? How many packs are needed? As Josh mentioned, how many levels of redundancy do you need? Even the form factor could play a role into the safety of the pack, whether it's pouch or cylindrical or prismatic type geometries. Performance and degradation of those batteries, as Jesse mentioned, it's not a linear thing to understand how these batteries will actually perform during flight and over time. So how long of a flight can these packs last? What kind of duty cycle can they be stressed under? Is active thermal management a requirement for charging and discharging? And will the batteries last a long time or a sufficient amount of time? And then in terms of the safety directly, how hot does the pack get during flight? Is thermal runaway a concern? And if it has to be tested against DO-311A, how are you going to go about ensuring that it meets the standards? Is the pack going to be a vented pack or an unvented pack? So these types of questions, obviously there's a tremendous amount of testing that goes forward in designing these packs and developing them, but multi-physics simulation can also address a lot of these challenges hand in hand with testing during development. And so when we talk about multi-physics safety simulation, it really is a multi-pronged solution in the sense of when you look at battery systems and battery safety, there's multiple physical domains when you're trying to represent those types of systems. And so if you think about, the batteries in an electrical system, there's a powertrain system that the pack is hooked into. And so it's required to construct an electrical circuit and represent those different powertrain components, not just the battery, but the motor, the inverter, and the other components that go into that system. And then when we look at the battery itself and understanding and trying to predict the performance instead of relying exclusively on test data with empirical models, there's an electrochemistry module that can be used to predict based on the cell chemistry and the geometry of the cell itself to predict the performance, not only the state of charge, but also the state of health. So you know how the capacity of the battery is changing over time. These batteries get hot, they're stressed quite hard, and during flight and during charging and so forth. And so understanding how the heat gets dissipated out of these batteries and regulating that temperature to put it in the sweet spot where a battery likes to operate, it's critical to have a thermal model that represents the different modes of heat transfer, whether it be conduction or convective cooling and even radiation. And that could be done, with a very simple type of thermal analogy or full 3D finite element of the entire system. For actively cooled packs or even passively cooled packs, the fluid surrounding the packs is important. Whether it's passively cooled with a fan, let's say it's air blowing over that, you want to understand how the fluid is affecting the thermal response of the battery. And if it's actively cooled, let's say it's a two-phase fluid or a single-phase coolant, understanding maybe how much flow you need to have if you're trying to regulate, again, from a thermal management perspective, is really important. But there's also mechanical aspects to consider as well. These batteries, they swell as they're stressed and as they're aged, and so how they swell and expand over time and their impact on the surrounding structure itself lends itself to trying to understand from a mechanical standpoint, well, what kind of pack structure do I need? How will that cell stress and strain affect the structure itself? And then the real beauty of multi-physics simulation is when you can integrate all these different domains together to build a comprehensive system level model. And that can go from a real detailed component battery type model to a full-blown vehicle level model where you're predicting flight range and so forth. Now, just to go into a couple case studies here about the example usage of simulation and its role on battery safety. And so if we step through a couple of thermal runaway examples here, one of these is with some known test data that was done by NASA a few years back, where it's looking at a battery module that was used on the Orion spacecraft. And this module here consists of 14 cylindrical type cells, and they're insulated from each other such that if one goes into thermal runaway, it tries to reduce the risk of other cell-to-cell propagation. And so the beauty of this was there was real test data that went into corner cell thermal runaway and middle cell thermal runaway. And then there was a model that was made side by side to compare how that performs. And so here you can see some test data where you have a corner cell, for example, heated up to the point of thermal runaway. That cell temperature spikes dramatically, but neighboring cell temperatures, the maximum is much cooler and never goes into thermal runaway. And so you can see these very similar trends in a predictive model utilizing the same test procedure where, the single cell, corner cell gets heated to the point of thermal runaway, but the neighboring cells are not affected because the insulation layer is doing its job. So now you could think about taking this simulation model and saying, okay, well, I did some expensive testing on a few cases, but what happens if I do, go through that process with each cell in the module? Or what happens if I change the boundary conditions? Something that wasn't tested could be easily simulated with a software. A second case is very similar, not just looking at a cell and module level, but this time looking at an entire pack. And in this case, it's a bus type application where you can see Rise out of Sweden created a thermal runaway test on an entire bus module where they used a burner to heat up one of the cells inside the module to the point of thermal runaway. And then there's actually eventual cell-to-cell propagation causing the entire module to go into thermal runaway. And then from there, it's looking at, okay, well, how can I suppress this with different strategies, whether it's external fire suppression or even internal fire suppression inside the pack itself. And so again, a physics simulation model was used to replicate what was happening in test. And so here's an example you can see of the module. Multi-physics simulation can give you insight on structure temperatures, on fluid temperatures inside, on individual cell performance and characteristics, whether it be state of charge, state of health, and so forth. And in the case of thermal runaway, understanding that cell-to-cell propagation. And so in this case, you could see there's a couple tests that were run physically, and the time at which they went into thermal runaway was different due to the way it was heated, but the trend and the duration it takes for all the cells in a given module to go into thermal runaway is replicated just like test. And so from there, again, that allows you to do model extrapolation to test, okay, what if I change the materials between cells, or what if I change the pack structure itself, or investigate different fire suppression strategies? How does that influence how this thermal runaway will go forward? Another great case in point is automotive companies like GM, for example, are, with the trend going towards electrification heavily in automotive, many OEMs are adjusting and transitioning to an electric mindset, and simulation is a very valuable part of that development process. And so tools like GT Suite, but also others with 3D CFD and so forth, are utilized to try to cut the production time and understand and save physical costs and so forth from a battery development standpoint. And things like thermal propagation are high on the list of concerns, and so that needs to be simulated. And there's a great keynote address on our website from a 2020 conference by Mike Anderson at GM. Another case in point directly related to eVTOL type application is looking at how a pack performs thermally, but also looking at state of charge and eventually state of health as well. And so with multi-physics, you can go in and dial in each individual cell inside a pack, and then run a model with a given flight scenario to see how that state of charge is changing over time, to see how the temperature inside the pack is changing over time. There's a really good case study that we did with Airbus's urban mobility department a few years back. And there's direct comparison to test here showing how the model reproduces the trend seen in test. And the beauty of that is kind of touching on what Jesse was mentioning a minute ago, where this nonlinear behavior of understanding how the pack will perform, how long of a duty cycle it will last for, how much range can you get out of the pack. It's not a linear thing like the traditional fuel systems. And so having a physics simulation model can help predict that even before you run that flight. And with modeling, there's many powerful workflows out there that allow you to build up models very quickly, especially if you have CAD data available. It's very quick to take an existing CAD model of a cell, a module, or a pack, and then discretize that into a multi-physics scenario and run it and do post-processing on 3D shapes and so forth. And so this type of analysis can be done in a practical time frame for fast turnaround to look at design space exploration. And there's much more in terms of safety simulations that can be done. You can look at full-blown 3D CFD and understanding how vent gas might propagate inside a pack, and looking at things like chemical reactions to try to predict the heat released during thermal runaway. There's also the ability to replicate testing such as DO311A or doing nail penetration type tests on a given cell. And with simulation, you can explore the design space very quickly. So that lends itself to looking at things like Monte Carlo analysis and variability studies to say, okay, well, the resistance, from cell to cell might be different, or the state of charge initially from cell to cell might be different. If I look at, a range of potential scenarios, how will that affect the response of the system, taking that variability into account? And then from a safety standpoint too, understanding how to design a pack for venting considerations, what size check valve you might need, or how does the pressure build up inside a pack over a given design, and so forth. So with that, I want to thank you all for your attention, and we've got some contact information here as well in case you're interested in learning more.
Awesome, John. Thanks so much. So if we can now bring everyone back on screen, we have questions that we're going to run through for everyone. Hi, guys. So Josh, to kick it off, we have a question. When you say high voltage battery system, what is the voltage range?
Yeah, that's a good question. The term high voltage can be a little bit dependent on your background and the context, but the battery systems we're talking about are typically like 500 to 1,000 volts without being, real specific.
Great. Another one for you, Josh, from Cameron Spencer at Flutter. What is typical cell life, and what percentage of charge are you defining as the end of usable cell life?
Yeah, that's a great question. So cycle life is really going to depend on the cycle, on the duty cycle, and what you're asking of the cells in terms of depth of discharge, the C rate, the temperature they're going to see. It's highly dependent. But if I could just throw something out there, we're talking in the thousands of cycles. We need to be up in the thousands of cycles for most of these airframers to be able to close their business case. It's got to be in the thousands. Jesse might want to add something to that.
No, I agree. I need at least, many thousands. And the batteries come off, our battery will nominally come off 85%, right? So 85% is end of life for us.
Great.
Yeah.
One for John. How does your model compare with Python's battery mathematical modeling?
Well, I do realize there's a number of tools on the marketplace for battery safety simulation. We really like to pride ourselves not only on things like safety simulation, such as thermal runaway test replication with modeling, but also from an electrochemistry standpoint to do cell predictions of not only state of charge under a variety of conditions, but also state of health. So there's the various aging mechanisms inside the model. And so with PyBAM directly, I don't think we've ever done a direct head-to-head comparison, but we do know there's other tools, and GT definitely has some core offerings that distinguish it from others.
There's a question from Rex Alexander. I don't know who this is for, so you guys can feel free to jump in. Have you tested exterior vehicle water injection ports for rapid and direct thermal cooling and management in an accident scenario, similar to Formula E race cars?
I'll say one thing, and then maybe Jesse, if you want to jump in. But to do that, it would require copious amounts of water to extinguish a propagated battery pack, but there would need to be a system trade that was done at the aircraft level to evaluate, the efficacy of incorporating those features into the aircraft design. But BAE is really focusing on solving the thermal runaway problem at the fundamental physics level. So I would maybe use the term a little bit more proactively, trying to solve this problem. Jesse, would you like to comment on that?
I mean, we have our initial cooling designs for both, operating the aircraft and for charging the aircraft. And, we haven't got to a point, obviously, in the development to see what the impacts of a crash sequence might be. But then again, like Josh said, there's system trades. If you start putting systems on there to be able to have some first responders do something like that, then, you have to look at you have to go back to the drawing board and look at the big picture and what that means, right? And if there are other ways to solve the problem.
Great, thank you. One for whoever wants it, maybe John or Josh, from Dana Jensen, US Air Force. How accurately can the battery management system estimate state of charge in terms of positive or negative percentage?
So our BMS is typically going to be able to fall within 1% of the true state of charge. And of course, it depends a little bit on where you are in the scale of 0 to 100. But that's typically where we are, which is pretty good.
Great. Another one for whoever wants it, from Miguel Iturmendi. Is altitude an issue with battery internal pressure and differential with the outside partial pressure at high altitude?
Hey, Josh, I'll kick that over to you. I know it's not, altitude is not a concern right now for these AAM aircraft. I asked Josh this question, and I was like, when we say altitude, what's altitude, right?
Right.
And when you're talking 8,000-10,000 feet and below, it's really not altitude.
Yeah. So I would say the answer to the question, is it an issue? Definitely for higher altitude aircraft, and you need to accommodate that pressure differential, and that falls into the design of the aircraft and having a robust burst disc design strategy. But yeah, it definitely falls into the equations, but it's important for the higher altitude aircraft.
Okay. I think final one from Terry Spruce. How close are we to making electric powered flight?
I'm sure we would all answer this and say it's within the next couple of years. I think, as Jesse has mentioned at the end of his talk, that even with today's battery technology, we're very close. So it's going to be within the next couple of years.
People are flying on electric vehicles right now. They're just not vertical takeoff and landing vehicles. So if that's any indication, I mean, the future is as close as here. When aircraft start getting certified, these vertical takeoff and landing aircraft start getting certified, it's going to become a reality. So we're already flying planes electrically.
Absolutely. John, anything to add?
No, nothing to add on that. It's just it really is exciting to see all the people in this space too. Electric vertical takeoff and landing. I think that's also a testament to knowing that the future is very close to becoming reality.
Great. We actually have one more question as we've been just doing this final question from someone in the audience. What is the weight ratio of cells versus non-cell components in BAE battery pack developed for Jaunt? I guess that's quite a specific question, but feel free to take it as you will.
I don't really want to comment on specific applications at this point.
Okay. I thought as much. Great. Well, thanks so much. Josh, if you have any final thoughts, happy to have that now.
Yeah, so I'm just really thankful for this opportunity to present and to work with Jesse and John and the Revolution.Aero team. And really, I just welcome any further conversations that others would be interested in, and more information. I think we'll have a link to the information for our business development lead, Justin McClellan. He's has a lot of knowledge about our capabilities and our systems, and he would be a great contact point to set up any further discussions that anyone will be interested in.
Definitely, and we also have a session with him at our last global conference, so we'd be happy to send up, provide the link for that. Well, thanks so much to you guys. Thanks again to BAE Systems for sponsoring. Jesse, Josh, and John, thanks so much for your time. Really appreciate you joining us today, and have a good evening. Take care.
Thank you.
Thanks very much, guys. Bye-bye.
Bye-bye.